This is video 5.2.2 to go along with section 5.2 in your book, which is on the sum and difference formulas. So we're going to continue to use those to solve problems, to find exact answers, and to verify identities. Let's take a look at this information. I'm going to let you read it over on your own. So pause the video here, read over the information and the first two questions. Okay, hopefully you paused it and looked it over. We're going to take a look at sine of alpha and use that to help us draw a picture of alpha. Since alpha is in between pi over 2 and pi, I know it's going to be an angle over here. Alpha is actually this large obtuse angle. So this is important because while my sine is positive, some of my values will be negative. The right triangle that corresponds here will have a height of 4 and a hypotenuse of 5 because the sine of that angle is 4/5. Now my leg on the bottom I do not know, but I recognize a Pythagorean triple. It will be 3. In this case, -3 because it's in the second quadrant. X is negative in the second quadrant. So I've represented sine of alpha, and that's really important because now I can find cosine of alpha. I have cosine of alpha here is the first question being asked, and I can see the answer is -3/5 because that's the adjacent over hypotenuse, or x over the radius, which is a non-unit circle definition of my trig functions. Take a look at beta, sine of beta, this information that you see here. Try to draw a picture, pause the video, and check your answer when you're done. Hopefully you drew a picture like the following to represent beta. It's going to be in the quadrant number 3 because of this information here. So we're going to use quadrant 3, and we have a rather large angle. And we're using the non-unit circle where this is the y value over the radius of this non-unit circle. So we have -2 square root of 5 over 5. Now taking a look using Pythagorean theorem, it will be important to get this x value. So I'm going to find the x value by using Pythagorean theorem and doing -2 square root of 5 squared plus x squared equals 5 squared. This side will be easy. It'll be 25 equals x squared. It's really important to carefully multiply out 2 square roots of 5 times -2 square root of 5, or carefully use your calculator. But notice it's a negative times a negative, so it'll be positive. And I can write multiplication in any order, so I'm going to multiply 2 times 2 and get 4. Square root of 5 times square root of 5 gives me 5. It's still a product, so I'm going to get 20 plus x squared equals 25. So I'm replacing the -2 square root of 5 squared with 20. I continue solving for x, and I get x squared equals 5 by subtracting 20. X is the square root of 5. Now that's perfect, except for the fact that I need to change this answer to negative because of the location of the x in my picture. So I see the x in my picture is in the left side of my coordinate plane, so it's going to be -square root of 5. So I have my value for x, which helps me with finding the cosine of b of beta. That was my ultimate goal here, so my cosine is the x value, -square root of 5 over the radius, 5. Okay, so let's take a look at the next two parts of this example. There are 2 more questions that go along with this example that lead us into our sum and difference formulas. Now we want to find the cosine of alpha plus beta and the sine of alpha plus beta. So I'm going to leave up a lot of my work here. I'm going to erase this Pythagorean theorem so I can more easily see what I'm doing. But I'm going to leave everything else up there. So looking at my sum and difference formula for part C, the cosine of alpha plus beta, I'm going to need to look at my sum formula, which we see at the top here, right in there. So it looks like I'm going to, since I'm adding, I'm going to subtract these 2 quantities. So I need to do cosine of alpha. Cosine of alpha is here. So in this case, it's -3 over 5 times the cosine of beta, That's the next piece. So times the cosine of beta, which we saw was negative square root of 5 over 5. And then the formula continues with a minus the sine of alpha, so minus the sine of alpha. Well, that was given to us at the very beginning. So 4/5 is the sine of alpha times the sine of beta, which was also given to us at the beginning. Here's the sine of beta, and here's where it asks in the formula. So times negative 2 square root of 5 over 5. Now it's just a matter of simplifying it out and figuring out what these different pieces equal. So this, when I multiply this out, I'm going to get negative, oh wait, negative times negative will be positive, square root of 5 times 3 over 25. This next piece, when I multiply it out, will be 4 times negative 2 times square root of 5 is negative 8 square root of 5 over 25, and that will be subtracted because of this here. I noticed that a couple of things. I noticed that I'm subtracting a negative, so I'm going to change that to adding a positive. I also see like denominators, so I'm on the right track. It looks like I'm going to add 3 square roots of 5 plus 8 square roots of 5 in the numerator and get 11 square roots of 5. Think of square root of 5 like an x value. It's kind of like the 8 and the 3 here are coefficients of that x value, and we want to figure out how many square roots of 5 we have, and we have 11 square roots of 5 over 5, 25. So the next one, sine of alpha plus sine of beta, we'll continue to use the same problem. So I'm going to pause here. I'm going to let you try part D on your own using the sum and difference formula and the 4 values we found here. So take a moment to do that. I'll scroll up so you can see the sum and difference formula for sine. Pause the video, try it on your own, then check back for the solution. Okay, as you can see here, the worked out solution listed here is listed for you to see how to get the final result of 2 square roots of 5 over 25. So pause the video, look over the notes, try to color coordinate things so you can find out where I got the different values, but I used the formula as you see at the top there and highlighted in green. So I'm going to move on to the next example. Pause here if you need to see more. So let's take a look at the next example. Now we're working with verifying identities. So we're going to use these sum and difference formulas whenever we're working with multiple angles like alpha and beta like you see here, especially when they're inside of a function like cosine of alpha minus beta. So the left is definitely a little bit more complicated. I also realize I'm going to quickly change it out so that alphas and betas are separate within the cosine. And I'm going to use the difference formula for cosine because of what my problem states, and that means I'm going to add these two quantities. So I'm going to start with the left side, cosine of alpha minus beta over sine of alpha sine of beta. And I'm going to use that difference formula to transform the top. So the bottom is going to stay the same for now. And I'm going to transform the top according to the formula. So it's going to give me cosine of alpha cosine of beta plus sine of alpha sine of beta. So I have all sines and cosines, that's helpful, and I don't have any sums or differences inside of the function like I did at the beginning. So I take a look at my goal. My goal is to get cotangent A times cotangent B plus 1. Now, if I want to do that, I see that these are two separate terms, but in essence right now, I have one big term, one big fraction. So I'm going to start by separating the fraction into two pieces. So remember, you can do that by taking your value here and separating the bottom will be one fraction, and the other fraction will be what you see on the top here. That will be the other fraction. So I'm going to separate it out into two different fractions with the same denominator. So this fraction will turn into cosine alpha cosine beta over sine alpha sine beta plus sine alpha sine beta. Let's take a look and move this here. Sine alpha sine beta over sine alpha sine beta. Well, look at that, I'm closer to my goal. Because this big quantity that I created with the left side of my fraction just equals 1, just like I want it to. So I can quickly simplify that to plus 1, this value right here. Now the left side, let's see, is that equal to cotangent of alpha over cotangent and times cotangent of beta? If you look at your identity sheet, this right here is cotangent of alpha, this right here is cotangent of beta. So I've arrived at my goal. Cotangent alpha, cotangent beta, plus 1. Let's take a look at another example. This one deals with verifying the identity of alpha plus pi. Tangent of theta plus pi equals tangent of theta. So I'm going to start with using my sum and difference formula because that may or may not help me, but at least it separates it because apparently I need just tangent of theta at the end. So I'm going to use the sum formula, which involves adding on the top and subtracting on the bottom. So tangent of theta plus pi will equal the tangent of theta plus the tangent of pi all over 1 minus the tangent of theta tangent of pi. So let's think about what this means. According to our unit circle, the tangent of alpha of pi is just 0 because the slope at pi is 0. So this quickly simplifies the bottom to be 1 minus 0 because anything times 0 will be 0. So on the bottom, I'm just going to have 1. And on the top, I'm going to have tangent of theta plus 0, as you see here. Well, that's just tangent of theta. And once again, I've arrived at my goal by simplifying this fraction and just simply writing it as tangent of theta. So that one was also quicker than it looked. Let's take a look at one more verifying identity just so you can get more ideas and skills. The final verifying the identity is the tangent of the quantity theta plus pi over 4 equals the cosine of theta plus the sine of theta all over the cosine of theta minus the sine of theta. So this one gets problematic because we have tangents turning into cosines and sines. This one will take a little bit longer. But we're going to start once again with the sum and difference formula. And since it's adding, we'll add on the top and we'll subtract on the bottom. So take a moment to try and transform that. I'm going to pause the video and give you a shot at trying that on your own, and then I'll reveal the solution after you restart the video. Pause it now. Okay, take a look at what I have written here. Hopefully you have the same thing. We're going to quickly solve this by starting out with taking tangent of pi over 4 out and replacing it with 1. The slope at tangent of pi over 4 is 1 according to our unit circle. So tangent of theta plus 1 all over. We do the same things here. This time it's timesing by 1, so we're going to have 1 minus the tangent of theta. Now let's take a look. We want sines and cosines to come into the mix. So let's take a moment to change out tangents into sines and cosines. So I want you to replace that with sines and cosines and that. Pause the video here, try that on your own, then check back for the answer. Okay, this next step, check your work here, make sure you have the same thing as I do. This next step is the interesting one. This is an idea that I have for you to simplify things. So when I see a denominator here and I don't want to make common denominators, a quick way to get rid of that denominator is to times the whole top by cosine of theta. That will allow me to cancel for this first part. However, it will not allow me to cancel for the second part. So I'm going to take the top and I'm going to multiply the whole quantity by cosine theta. To keep it balanced, I'm going to multiply the bottom by cosine of theta as well. And that will give me sine of theta plus cosine of theta all over cosine of theta minus sine of theta. Okay, so then the final thing I'd like you to do is take a look at the checkpoints, bring them into class tomorrow.